Welcome back. In the previous class we talked about the self interaction energy within the film, and based on that we derived an expression for the effective Hamaker constant for a situation like this, where you have a film of, let us say, liquid 2 on a surface of liquid 1. Now what we are going to do, we are going to look at the old problem of two blocks of 1 and 2 coming in contact with each other in a medium 3, and all we consider is, both in terms of self energy as well as interaction across different objects, is we consider pure van der Waals interaction or the London type interaction. And we understand that the nature of this interaction is always attractive, but we will see that in this particular system there can be a situation where even based on pure van der Waals interaction you can have an effective repulsion between 1 and 2. So, let us identify the system. Unlike the previous system, we have two semi-infinite blocks of 1 and 2, which are coming in contact with each other, displacing a layer of 3, which is the thickness of which is d. Okay. So, the self energy of interaction of block 1 is A11 divided by whatever is its thickness, 12 pi d1 square. Self energy of block 2 would be A22 divided by 12 pi d2 square. Now, since both are semi infinite, therefore, both d1 and d2 tend to infinity, and therefore, both this term and this term tends to 0. Self energy of 3 is of course minus A33 divided by 12 pi d square. The interfacial interaction between 1 and 3 is minus A13 divided by 12 pi divided by 1 by d0 square minus 1 by d0 plus d square, which can be approximated as minus A13 divided by 12 pi d0 square minus 1 by d square. Assumption is d is much larger than d0. Similarly, the interfacial interaction between 2 and 3 will lead to minus A23 divided by 12 pi divided by 1 by into 1 by d0 square minus 1 by d square. And the interaction between 1 and 2 if you look at this term again between 1 and 2, so the minimum separation distance is d, d1 tending to infinity, d2 tending to infinity. So, that is given as minus A 1 2 divided by 12 pi d square. So, these are the 4 terms that remain active. The self energy of interaction of 3, the interaction between the molecules of 1 and 3, the interaction of between the molecules of 2 and 3, and the interaction between the molecules of 1 and 2. Of course, you can immediately understand that if the layer, the liquid layer 3 is very, very thick and wide, then 2 of the terms disappear, that is the self energy of interaction of 3 tends to 0, because D is very, very large, as well as the interaction, the interfacial interaction, or the interaction, not exactly an interface, the interaction between the molecules of 1 and 2 also tends to 0. There will be only local interfacial interaction between 1 3 and 2 3, because these 2 terms still remain active, because D might be very, very high, but this D0 square, this is a small, this is small. So, these terms remain active. So, considering these 4 interactions, the GLW of the system turns out to be minus A33 divided by 12 pi d square minus A12 divided by plus the constants. So, we are interested in the change in the energy, and therefore, the constant does not matter, or we are interested in the change in the energy as a function of D. So, the constant really does not matter. So, we can neglect it. So, therefore, we can write the GLW of the system is minus AE pi d square, where AE is the Hamaker constant, and in this case has an expression of A33 plus A12 minus A13 minus A23. We should not sort of confuse this Hamaker constant, the effective Hamaker constant, with the previous one. So, I guess it should be better to write something like this, A132. We have talked about this convention of 132 before, where 1 and 2 come in contact with each other by dislodging the liquid 3. Okay. So, we can write that what we already know, that A12 in one of our previous classes we have shown that it is A11 into A22. A23 similarly can be written as A22 into A33, and A13 can be written as A11 into A33. So, in that way, what we can write here, or if we plug in this expression and do a little bit of algebraic manipulation, you just have to consider the first term, third term, you club the first and the third term together, the second and the fourth term together. What you get is, eventually if you do the simplification, you would be getting an expression like this. This is the effective Hamaker constant. Now, we know that the GLW of the system is minus AE divided by 12 pi d square, and we also know from the force curve that any interaction is attractive as long as it remains negative. So, this interaction will remain attractive only when AE will be positive. Okay. So, if we simply argue that the condition, or let us write it down here in a fresh okay. And if we write down the condition for attraction, attraction between what? Condition of attraction between 1 and 2. So, we had argued that since the interaction is van der Waals based on van der Waals interaction, therefore, in air the interaction between A and 2, 1 and 2 will always be attractive. Okay. But now you have a liquid 3, we are not considering any polar interaction or anything like that. We are only considering the interaction, the van der Waals interaction, but the interaction between 1 3, 2 3 and 3 3. Now, the condition of attraction between 1 and 2 remains that the GLW of the system has to be negative. Or in other words, therefore, AE has to be positive. Okay. Now, you see in this particular case, the expression of AE is given as therefore, you can see that if AE or A33 lies between, it is simple mathematics, if A33 lies between A11 and A22, then AE will be negative. This can also be written in terms of the surface tensions as AE is equal to 24 pi d0 square into under root of gamma 3 LW minus under root of gamma 1 LW into gamma 3 gamma 2 LW, and the issue would be if gamma 3 lies between gamma 1 or gamma 3 LW lies between gamma 1 LW and gamma 2 LW, then you will have AE to be equal to negative. In the event that gamma 3 LW is greater than both gamma 1 LW and gamma 2 LW, or gamma 3 LW is less than both gamma 1 LW and gamma 2 LW, you will have a positive AE. Okay. So, this is now you can see that depending on the relative magnitudes of the surface tension, the van der Waals component of surface tension, you can have an interfacial attraction or repulsion between the two blocks 1 and 2, even though we are considering only the van der Waals interaction. The other interesting thing is that we say that the condition for attraction is AE has to be positive. So, in that case the 1 and 2 will get attracted towards each other. So, this is an important point. So, a condition for attraction, I would just reiterate this one, condition for attraction is AE is positive, attraction between 1 and 2. So, they will come in close contact with each other by dislodging the film of 3. So, in other words, this is, though this is a condition for attraction between 1 and 2, this is also a condition for the film to be unstable. Okay. So, a positive value of AE will result in the film to become unstable, and if you now refer back to this old slide which we prepared in the context of explaining to you spreading coefficient, you find exactly the same thing. A positive value of AE refers to a thermodynamically unstable film. So, the film essentially ruptures. So, essentially we are talking about the same thing, same scenario, only difference is here we talked about a separate liquid film coated on a rigid substrate, and here we are talking about a liquid film which is sandwiched between two solid surfaces which try to sort of come in contact with or sort of disappear. So, the condition for instability here is manifested by an attractive interfacial interaction. Same thing is valid here, a film will become unstable if the interfacial interaction is attractive. And what is the interfacial attractive? What is the interfacial interaction here? The interfacial interaction is the between this liquid air interface and the liquid solid interface. In contrast, here the interaction is between two liquid solid interfaces. So, the condition for attractive interfacial, or in other words, attractive interfacial interaction invariably results in rupture or disintegration of the film that was separating the two interfaces. Okay. We will understand this in greater detail, but again let me just quickly tell you what is the basic essence of this. So, we are doing this apparently very simple calculation here, trying to find out the condition. We are talking about two blocks 1 and 2 which are coming in contact or trying to come in contact through liquid 3, and in order to do that, if they want to come in contact with liquid 3, there can be two ways to visualize it. One of the possible ways is to there must be an attractive interfacial interaction between 1 and 2, but the other way of looking at it is that the film of 3 has to sort of disintegrate, because there is a layer of 3 which is between these two surfaces, and if these two surfaces wants to come in contact, first thing is the two interfaces. If you now look at, instead of looking at the two blocks, if you now look at from the standpoint of this liquid layer, its two interfaces are the 1,3 interface and the 2,3 interface. So, these two interfaces have to be attractive, the 1,3 interface and the 2,3 interface, and these two interfaces, in order to favor attachment, the 1,3 and the 2,3 interfaces must be have attractive interaction. Okay. So, the moment these two have attractive interaction, of course, the blocks 1 and 2 would come into contact, but what will happen is that the film that was initially separating the two blocks 1 and 2 has to sort of disintegrate and disappear or rupture in favor of attachment of these two interfaces. So, essentially the two separate interfaces, the 1,3 and the 2,3 interfaces would like to merge to form a new 1,2 interface at the cost of disintegration of the film 3, which was isolating the 1,3 and the 2,3 interfaces. So, one way of looking the condition at the film between the two has to be unstable, or a film will be unstable if there is an attractive interfacial interaction between its two interfaces. Exactly the same thing happens when we are talking about a film which is coated on a rigid surface. So, here we so let me draw it in a neater sheet of paper, so that you do not confuse it. So, here we have a film, here we have a substrate, and we have talked about discussed about adequate experimental techniques like spin coating, dip coating, which can result in a film like this. Okay. Now, the question to ask is, whether a film created like this remains stable over a prolonged period of time or it disintegrates. The answer to that is it depends to a large extent on the nature of interfacial interaction. What is meant by interfacial interaction? It is the whether the interaction between the film air interface and the film substrate interface, whether this interaction is attractive or repulsive. Depends on that. So, if the interaction is attractive, of course, then these two interfaces will try to merge with each other exactly in the same fashion as here, where the two interfaces tried to merge with each other by preferentially draining off of the liquid film or by dislodging or disintegrating the liquid film. In contrast, if the interfacial attraction is repulsive, then the film layer remains intact. Exactly the same thing happens here as well. If the interfacial interaction is repulsive, then which we have also understood that it happens under a situation where a, so let us write it down somewhere. Okay. So, a repulsive interaction between 1, 2 and 3, between 1 and 2 results when we have seen that gamma 3 lies in between 1 and 2. If gamma 3 is less than both gamma 1 and gamma 2, or gamma 3 is greater than both gamma 1 and gamma 2, then of course, the interaction between 1 and 2 is attractive. One can also explain in this way that this interaction, irrespective of the magnitude of 1 and 3, will be always attractive. As you cannot have a value of gamma 3 which is between gamma 1 and gamma 1. So, it will either be gamma 3 will be higher than gamma 1 or it will be lower than gamma 1, but irrespective of the case, the interaction will be attractive. So, a repulsive interaction, this is the necessary condition for a repulsive interaction. So, the repulsive interaction also implies that the film or layer of 3 remains stable. So, we are talking about instability, or eventually we will be talking about instability. Two things are getting attracted, dislodging a liquid layer in between them, that is fine, but that is also so here if they come in contact or the interaction is attractive, then 1 and 2 join up, but this also leads to drainage or disintegration of the film. So, we can start developing our own rule of thumb or based on our understanding, which is of course fundamental understanding. Any attractive interfacial interaction results in film instability. In contrast, if you have a repulsive interfacial interaction, would like to have a film stability. We just gave an example that the same thing is valid when you have a film which is coated on a substrate. So, repulsive interfacial interaction, what we have written here. So, repulsive interfacial interaction leads to film stability. Exactly over here the same thing, these two interfaces repel each other. So, the film remains stable. So, this concept what we have written here remains valid irrespective of whether your setting is like this or like this. So, a repulsive interfacial interaction will lead to a film stability. In contrast, an attractive interfacial interaction will lead to a film instability. We will talk about this in greater detail when we do the thin film equation. But right now, we will talk a little bit about another aspect of this attachment. So, what we have talked so far or drawn so far is something like a geometry like this, where the surfaces are sort of flat and parallel, okay, and we have talked about their attachment or the condition of their attachment. But let us now try to understand or identify the condition or this what happens when two surfaces of arbitrary geometry try to come in contact with each other. So, for this type of a setting, we now have the expression for phi or the GLW of the system in very clear terms, which is essentially minus AE 12 pi into whatever is the separation distance, okay, depending on d. Between two surfaces of arbitrary geometry, what is the important thing or the important deviations? So, here the interfacial interaction per unit area is a function only of the separation distance. What happens here? The total energy of interaction depends on the size, and effectively, so phi becomes a function of the effective Hamaker constant into function of geometry. Now, if we have seen from this system that whether you replace the vacuum or air by another medium, only the magnitude of A changes, but this geometric parameter remains unaltered, which for a definite geometry were of the form like this. So, whether you if you change the medium, let us say you plug in a liquid 3 over here, what will change is this one will change, but this remains unaltered. So, same thing is valid over here also between the interaction of between particles of arbitrary geometry. If we consider the interaction between two spherical particles, let us say of radius r1 r2 and the separation distance is d, then one can get this derivation is beyond the scope. One gets that A is equal to A, the phi is equal to A by 6 into 2 r1 r2 a little longish expression. Okay. And important thing to note is this is not per unit area, but this is the total potential. Therefore, what we can write that it becomes a function of A into essentially there are 3 parameters r1, r2 and d, but what can be seen that it can be sort of resolved as a function of r1 by d and r2 by d. So, 2 geometric parameters. So, these two are spherical particles. So, there is an angular symmetry over there, but if you take any other type of particles, even let us say cylindrical particles, these type of angular symmetries will be missing, and there will be need to introduce more geometric parameters. So, what is important to note or interesting to note is that for spherical particles the van der Waals forces scale up with r1 by d and r2 by d. So, if r increases by 100 times and d also increases by 100 times, the sort of the magnitude of van der Waals forces remains roughly the same. So, in a practical setting in let us say the colloidal domain, what we have r1 and r2 much larger than d. So, therefore, taking asymptotic limit, one gets and for the specific case R1 equal to R2, one also gets phi is equal to minus AER divided by 12D. Hence, the decay of van der Waals force is with separation distance is 1 by D. So, this is very interesting now. So, we know that the decay was as 1 by x to the power 6 for particles or molecules or atoms. For two parallel surfaces, the decay sort of reduced to 1 by x square or 1 by d square. But now we see that the decay between two spherical surfaces, the decay of the non-retarded van der Waals force between two spherical surfaces is as a function of 1 by d, which means that the decay is even more sluggish as compared to the particles or between two parallel surfaces, or in other words, the force here becomes much longer range. Okay. For complicated geometry, of course, we do not have expression for the intermolecular interaction or for AB type interaction, and therefore, when we talk we need to sort of identify or we need to identify the actual forces. The force measurement module of the atomic force microscope which we talked comes in handy. But what we have is that the geometries that we have understood are that we have an expression of interaction between two parallel plates and two spherical surfaces. But even if you are measuring the force, okay, between two surfaces using an atomic force microscope with a colloidal probe, you are actually leading to this situation. So, you have a spherical probe and you have a flat surface. Okay. So, this force can be sort of quantified based on what is of course, the AFM based on an approach or an approach and withdrawal, you will generate a force curve. But in order to convert that force curve or extract the relevant information to convert that force into the exact potential, you need to use what is known as the Derjaguin's approximation. So, this is a critical concept of soft condensed matter physics. I will cover it in very brief detail. Just it is important for you to know the existence of Derjaguin's approximation. Even if you find understanding it a little bit difficult, does not really matter. You can refer to any standard textbook or the internet for finding out what it means. So, it essentially in a nutshell, it talks about the interaction of two spherical surfaces of same radius of curvature and then assumes one of them to be having an infinite radius of curvature, or one of them to be flat, and tries to develop an expression for this setting for phi, expression for phi for this setting, and which if you now measure the force or get a force distance curve using an atomic force microscope, matches exactly the situation, because eventually Derjaguin's approximation gives you how to measure the phi between one curved surface and one flat surface, and in an atomic force microscope we have already talked, if you are using a colloidal probe you exactly have that setting. So, we consider two curved surfaces. Of same radius, let us say r. So, it is like this, and so this is the axis. D is the gap between the two surfaces, and r is much greater than d. Critical assumption is two is a flat surface. Okay. So, we consider just the way we talked about a surface element while deriving the expression for Young Laplace equation for a axisymmetric surface. We consider a surface element ds, and this particular zone, if you look carefully, this is nothing but d minus h by 2. This is h. This is h. So, this is d minus h by 2, this particular zone, and what we have is d phi is delta g as a function of d, the separation distance. Okay. Now, delta g d is the energy per unit area of interaction of a particle of 2 with a ring of area ds of particle 1, of particle of 2 with a particle of 1 which lies within the area ds. And you can also see from simple plane geometry that ds turns out to be 2 pi y into under root of 1 plus dz dy whole square into dy. Since the curvature, now since the is small, therefore, dz dy can be regarded as much smaller than y, and therefore, phi is delta g d into 2 pi y dy. Next, we need to know d as a function of y. Now, from the right angle triangle over here, we know or we have r square minus y square is equal to r minus d minus h by 2 whole square. So, this is r square. So, it is essentially y square plus this amount, which is r minus d by h by 2. Okay. So, this is Pythagoras theorem. So, this plus y square is equal to r square. So, if we differentiate from the both sides, we get 2 y dy is r minus d minus h by 2 into d d, r is constant. Therefore, 2 y dy is under root r square minus y square into d d, which turns out to be r into 1 minus y by r d d. Okay. Now, consistent with all the approximations we have made so far, as y becomes comparable to r, the energy of interaction decays. So, y by r becomes much smaller than 1. What we want to do is we would like to retain the interaction in the vicinity of the minimum separation distance. So, the idea is that if we take the assumption y by r much smaller than r, we actually want to retain the interaction in the vicinity of the minimum separation distance intact, and we neglect the interaction at greater distance, but the error, as the interaction anyway reduces with increased separation distance, the error remains still small. And in so therefore, what we have is 2 y dy is equal to r d d, or in other words we get y square equal to r d plus c 1. We eventually can evaluate the constant as r into d minus h. So, we approximate the surface at the contact region to be a quadratic surface. The precise details of okay, before we move on, I mean I think that I need to quickly do a recap. So, Derjaguin's approximation essentially is aimed at generating an expression for phi and analytical expression for phi between a spherical surface and a flat surface. Why this? Because we have expressions for interaction between two flat surfaces and we have interactions available. We did not do the detailed derivation, does not really matter, it is not important, but it is important for you to understand what are the expressions that already exist. We have the expression of interaction between two flat surfaces, and we have the expression of the potential for interaction between two spherical surfaces. What is important that we would like to, so here we find that the interaction becomes a function of these geometric parameters, and also the fact that these are spheres, but more complicated geometries you bring in, the number of geometric parameters increases. So, it becomes pretty difficult, and probably one has to talk of think of the force measurement, direct force measurement using an atomic force microscope or a surface force apparatus to measure the forces rather than getting an analytical expression. But one of the critical one of the ways is to sort of find out an expression for phi between a spherical surface and a flat surface, and that is what is done using what is the objective of Derjaguin's approximation, or that is how it works. It is it sort of starts off by considering the interaction between two curved surfaces of same radius, and considers a surface element ds on the surface of the first spherical surface. So, this is the surface element which is at a distance y from this central line, which lies on the line where the minimum point of contact is. So, this is h. This zone is, since the two have the same radius of curvature. So, this zone is d minus h by 2. This is y, this is r, this is the center. So, here from this way, this is also r, and this distance will be r minus d minus h by 2. We will be using somewhere. So, it is important that you identify the Pythagoras theorem for this particular triangle, where we will find that r square, we will use that r square is equal to this particular thing square plus y square. Now, this is the surface element. I would strongly recommend you to look at the derivation for the Young Laplace equation for an axisymmetric surface to get an expression for this one, how this thing comes. Since the curvature is small, therefore, del z del y is much smaller than 1, and del phi is equal to delta g of d as a function of delta g d. Now, delta g d is the energy per unit area of, or energy per unit area of interaction of a particle of 2 with a ring, with a particle which is within the ring ds, I would say. Therefore, phi is equal to delta g d into 2 pi dy, that is delta g d into ds, which is 2 pi dy, under the fact that the curvature is small. And then we need to identify d as a function of y, and from the right angle triangle we find that, as we mentioned, we consider this right angle triangle where r square is equal to r minus d minus h by 2 whole square plus y square. That is exactly what we have written, and from that we get 2 y dy is equal to this particular expression. Now, consistent with all the approximations we have made so far, we understand that as y becomes comparable to r, the energy of interaction decays, that is far away from this point of minimum interaction. Y becomes comparable to r is y is large. So, you are essentially talking about these zones where the interaction decays, and therefore, we neglect this particular term and write that 2 y dy is equal to r into dd, and upon integration and substitution of the constants of integration at y equal to 0, you just plug in that d is equal to h, and therefore, you get this particular expression for y square, which gives you that the surface at the contact region, that is this particular region, is a quadratic surface, which is perfectly fine. The precise details of the surface is not that greatly important. What is important is the configuration of the surface near the vicinity of the point of contact, and therefore, we get phi is equal to pi r integral h varying between d varying between h and infinity delta g d into dd. This is a general expression, and which can be valid for all types of interaction, not only limited to van der Waals interaction, once you know the nature of delta g as a function of d. So, and it can further be extended for surfaces with unequal radius of curvature. We can have phi is equal to 2 pi r 1 r 2 divided by r 1 plus r 2 integral of h to infinity delta g d dd. So, this is the Derjaguin's approximation, but this is more of an important conceptually to understand that an analytical expression, it is possible to find out an analytical expression for this particular setting, that is the interaction between a spherical surface and a flat surface. So, with that we come to an end of this particular module, which is on intermolecular forces between surfaces and particles. We talked about the van der Waals interaction between particles to start with, then we talked about two parallel surfaces, and eventually we talked about the van der Waals interaction or the total interaction between surfaces with arbitrary geometry. And we also talked about the interaction, the self interaction of the molecules as well as the interfacial interaction, and based on that we tried to find out a condition under which a film becomes, or for the first time we talked about a condition in terms of the effective Hamaker constant that gives you an idea what can make a film stable or an unstable vis-a-vis what is the condition, necessary condition for the interfacial interaction to be attractive or repulsive, even if you consider interfacial interaction only based on van der Waals forces. Thank you.